Hello, and thank you for joining us. Today's webinar is Mercury Analysis within the Petroleum Industry, presented by Jeff Forsberg, Technical Product Line Manager for Teledyne Leeman Labs. This webinar is being recorded and will be available within a few days. Okay, so now I'll turn it over to our presenter, Jeff Forsberg.
Hi, everybody. Thanks for joining the webinar today. So within the refineries, why do we want to look for the presence of mercury and mercury species within refineries? Simply because the effects of mercury is ongoing and its issues in most refineries. The data, the global data indicates that the contribution from mercury emitted from the refineries is quite low. Air is about 0.07% of the global pollution load emitted each year, and about 0.01% for the water. So it's pretty low on that aspect, but that doesn't mean that we can't ignore mercury within the refineries itself. So if we turn a blind eye, then the refineries wouldn't know the risk. Within the refineries, the risk levels are quite high, so they need to know the mercury in the feedstock, and then also what species it is in the feedstock. And they would also need to know the levels of mercury in the distillation process and how that mercury is distributed across the boiling ranges within the refinery. Mercury accumulation in refineries can be very detrimental to the system. It'd be like pouring mineral acid on most metals. Typically, though, within the refineries, the crude coming in is around 0.2 ppb, but the potential for accumulation of mercury is quite high, and that could result in major operational issues. So with that, refineries should, one, know the contamination levels of the incoming feedstock, monitor the mercury levels to facilitate environment that is safe to work in, maintenance, perform timely maintenance to mitigate the mercury levels. And they also employ, most of them employ mercury removal technology. MRU, a mercury removal unit, could be something like a sulfur bed or that type of technology to remove mercury in the feed streams. And then also use approved waste management procedures for mitigation of waste within the refinery itself. Crude oil as a feedstock is typically priced by its components in that feedstock. An example, mercury-free crude is priced higher than crude that has levels of mercury in it as a contaminant. If a refinery chooses the less expensive route, then they must know and understand the risks associated with that contamination of mercury and the levels of mercury and the species of mercury within that crude. In sulfur-rich crudes, mercury will be very stable, and it's typically in the form of mercury sulfide. But when they heat that incoming feedstock and start the distillation process, it decomposes, liberating elemental mercury. So elemental mercury will combine with aluminum and its alloy. This is what we refer to as amalgamation. Because of this phenomenon, the amalgamation of mercury with aluminum, something happened. It's called liquid metal embrittlement, and for short LME. And this is a real problem within the refineries, because what it will do, it will significantly, the metal used in the piping can significantly lose ductility, its strength, and exhibit some brittleness, and then ultimately fracture. So within this process, if we have metal piping and stuff that fractures, then we can have a catastrophic event. Brass and copper alloys can also be affected by liquid metal embrittlement. If you go online, you can search this phenomenon. You can see some of the catastrophic events that have happened over the years at refineries, and they'll show pictures of piping and stuff that is just ruptured, and that usually leads to a fire and explosion. It can also, liquid metal embrittlement can occur in aluminum piping used to transport feedstocks and distillates within the refinery process. So it can happen everywhere. So it's something that has to be on the top of the list of what to watch out for. To mitigate the catastrophic risks, refineries typically are going to specialize in techniques for analysis of mercury. They want to look at the species and all the different fractions within the distillation systems. Elemental mercury and mercury sulfide are believed to be the main species in the refineries. Mercury is also known to have an affinity with petroleum distillates. So especially like the lighter hydrocarbons, the propane and butane would be an example of these fractions that can be affected. So wherever those fractions are heading within the refinery would be a place to watch out for LME. And it's also found to be present in condensates like the light oils. So that part of the fraction in the refining process would also be a point of concern. To mitigate the catastrophic risks within the refineries, they must select appropriate piping materials and ensure that construction of the materials themselves are not susceptible to LME. And this could be simply by trying to limit the bends in the piping, which will ultimately decrease mercury pooling in theory, so it doesn't start to drop out at cold zones or places where there's different restrictions in the flow. Other risks within the refinery from mercury can include most organic species are extremely toxic and require strict control of health, safety, and environmental measures. Mercury can poison platinum catalysts, which would make very expensive repairs within the system. And then also, if the workers are repairing pipes, mercury-laden piping can expose those performing the work to potentially toxic forms of mercury. Typically, some of the methods and their challenges for total mercury, you want to convert the species to elemental and or HD2+. A couple of techniques are combustion AA, cold vapor atomic absorption as well. So in those techniques, the combustion AA, you're going to collect and release via gold trap. For the CVAA side of it, you're going to reduce and release via liquid separation, liquid gas separation. A typical digest for these oils and distillates would be via microwave. It's almost impossible to use a block digestion and get oil or oil residues into solution with just permanganate and some of the other typical reagents that are used in block digestion. And then they're going to measure the emitted mercury, and this process doesn't give any species data for the original sample. It's just total mercury within these two techniques, combustion AA and cold vapor atomic absorption. Typical methods for total mercury. Several mass balance studies have been conducted using these methods. Mostly small amounts of mercury are found in the refined products. Also can be found small amounts in the air emitted from the systems. And the smallest amounts are found in the petroleum coke. Studies agree that trace levels of mercury, typically less than 1 ppb, nanograms per gram, are passed into the gasoline and or diesel fuel within the fractions in the refining process. But future studies should correlate the amount of mercury and sulfur entering the refinery stream. So do they correlate together? Does one or the other help the other one to reduce risk and or less sulfur in fuels and so forth? Low sulfur feedstocks tend to accumulate deposits of elemental mercury. So crudes with higher levels of mercury tend to distribute elemental mercury into the distillates and light streams. An example of a light stream would be liquid petroleum gas. When elemental mercury mixes with hydrocarbons, the vapor pressure is slightly different than from when it's in air. Therefore, it's going to tag along with the lighter distillate. So that would be a stream to pay special attention to, is the lighter distillate stream. And then on the contrast, when you have high sulfur feedstocks, they tend to accumulate deposits of mercury sulfide. So mercury sulfide has a lower volatility and therefore are less soluble within the streams from the refinery itself. So sleuthing the mercury in the refinery. Not all crudes are created equal. Global variances in crudes and condensates are extremely high. Some of the estimates range from 0.1 to 20,000 ppb. 20,000 ppb seems like a lot, but I guess it's probably possible in different regions and so forth. That's a 10 ppm concentration of mercury in the mass of oil. In refining, mercury concentrations in various streams are dependent on the concentration in the feed streams, which we've already talked about. Therefore, it's very important to know that concentration of the incoming feedstocks. Mercury can and will accumulate gradually within the process equipment. Therefore, most refineries try to limit the loads of certain levels of feedstocks with elevated mercury to try to minimize the effect of mercury depositing within the refinery itself, within the piping and mercury removal units and so forth. So accumulation of mercury can occur even when they employ the best practices for controlling the levels of mercury in the feedstocks. There's a potential for liquid mercury to accumulate in large and small refineries. It does not discriminate. Monitoring and mitigation should never be ignored to control the potential of mercury pooling. Once this starts, then LME is going to be very prevalent within the system, and it can lead to a very catastrophic event within the refinery itself, explosions and fires and so forth. Health and safety within the refineries. So here's the deal: short-term exposure to high concentrations of mercury can cause lung damage, diarrhea, vomiting, blood pressure and heart rate changes, skin rashes, eye irritation, and there's more that can be added to that list. On the other side of it, long-term exposure to low concentrations of elemental mercury can affect the brain and the nervous system. So the half-life of mercury in our bodies is in months. So even small amounts of exposure can be very toxic to the workforce and the employees in the refineries themselves. So how do we minimize exposure? So some countries have set workplace exposure limits, and those values vary by country. Here in the U.S., OSHA has set elemental mercury, inorganic mercury, to 0.1 milligrams per cubic meter. And that's an average weighted exposure over 8 hours. Alkyl mercury, this is your organic mercury, such as ethyl, methyl, and dimethyl, is 0.01 milligrams per cubic meter over a weighted average over an 8-hour exposure. But within that, there's a ceiling. It should never go above 0.04 milligrams per cubic meter. Aryl mercury, which is your long chain mercuries, such as your phenylmercury, that's the same as inorganic, 0.1 milligrams per meter cubed. And that's because they behave toxicologically similar to the inorganic species of mercury. Exposure routes within the refinery for workers. Most likely it's going to be inhalation during maintenance such as welding. So everything is encased in the piping and so forth. When they shut down for maintenance, changing out the mercury removal units and or working on those, that's when the exposure is going to happen. So an elevated risk is going to be during the change out on the absorber. Exposures is typically related to shutdowns. Therefore, exposures could be infrequent. During shutdowns and maintenance, it's highly encouraged that the workers have badges and handheld mercury monitors to measure elemental mercury during the maintenance of the shutdown. Also, it's not a bad idea to have biological monitoring for the baseline. So employees start, periodically you can monitor their blood and urine samples looking for mercury. And that'll tell you a lot about exposure within the refineries themselves. It's typically pretty inexpensive to do that, and it's good for the workers. How much mercury is present in feedstock? So this is process safety. What are the concentrations in the aluminum piping? Those need to be answered continuously. Charts and control charts need to be employed. They need to be looking at the historical figures for the refinery itself. Got to remember, mercury can condense via cooling in the heat exchangers, so all that is true. For monitoring, International Petroleum Industry Environmental Conservation Association, or IPIECA for short, is a global nonprofit group. And they estimate that the global average for mercury concentration in crude is approximately 7.5 ppb. Earlier, the United Nations estimated those values at 55 ppb. And the amount of air, amount emitted in the air and water is lower than what the United Nations Environment Program estimates. I think this is most likely, and some of the reports say it's most likely due to the affinity for sulfur, which may or may not have been calculated in some of the estimates. So monitoring, analysis, combustion, atomic absorption, CAA, we need to look at the feedstock, the finished products, and the waste streams. When you're looking at piping material during maintenance and or shutdown, maybe a handheld XRF might be the instrument of choice. It'll give you a quick reading right there and then. You should know what your risk levels are at that point. Thermal decomposition mercury analyzer. So this is the CAA. So here at Teledyne Leeman Labs, we have a system that's called the Hydro 2C. Direct determination of mercury in solids or semi-solids. Direct determination and at ppb levels, low ppb levels for aqueous samples, low ppb levels for petroleum distillates. There's no time-consuming complex sample digestion steps, no wet chemistry, with the exception of if we're going to run aqueous samples and you have the sample in a boat that is nickel and acidified with, say, nitric acid. The reason for the L15 is to capture the mercury and retain it in the boat. Acid and nickel is going to cause a reaction. You're going to have hydrogen gas liberated. And when that happens, due to the volatility, vapor pressure of mercury, some of the mercury is going to be lost. So it's going to leave the boat, therefore you'll have a biased low sample. So if you use L15, which is a thiol compound, it's going to grab the mercury, keep it in the boat, so you're going to get better analysis. One of the benefits also is we eliminate the toxic waste disposal. Basically, just have ash. The elemental mercury goes through the system and that's collected on the trap. So eventually that trap would need to be disposed of as toxic waste. But most samples, the level of mercury is so extremely small, it takes 6 months to a year or longer to consume the trap where it needs to be disposed of. some of the benefits of a combustion atomic absorption system, matrix independent analysis, validated method results for 3 methods, US EPA 7473, and 2 ASTM methods, 6722 and 7623. And then also a relatively low cost for analysis, less than $2 per sample. Typically, it's going to be just north of $1 and maybe around $1.50, but it depends on the cost of oxygen and some other things within your region. How much does it cost to run a tank, a dewar, and so forth. But for sure, less than $2 per sample. As I mentioned earlier, it's matrix independent analysis. So mass-based analysis, use one calibration, mass-based, one size fits all approach. Use one standard operating condition for most samples. You can also run multiple sample types automatically without operator intervention. Fast turnaround time. Analysis from sample in to reported values are moisture dependent. For dry inorganic samples such as fly ash or samples like that, dry coal, it's going to be in approximately 5 minutes or less. Actually, it's probably around 4 minutes to 4 minutes and 10 seconds, thereabouts. So 3 of the promulgated methods I mentioned earlier, US EPA 7473, total mercury in solid solutions by thermal decomposition, so amalgamation and atomic absorption spectrometry, ASTM 6722, standard test method for coal, for total mercury in coal and coal combustion residues by direct combustion analysis, and then ASTM 7623, which is the standard test method for mercury in crude oil using combustion, gold amalgamation, and coal vapor atomic absorption method. This can also be used for other types of petroleum samples as well. So our system is pretty basic, 7 steps. You basically load, inject, dry combust, purify, remove that moisture, collect, elute, and detect. And there's 7 sections within the system. Your sample boat goes in, combustion and dry furnace are all the same, and then catalyst over to the Nafion drying system, which was removing the moisture, off to the gold trap detector, and cells within the detector for measuring the mercury. So in that spectrometer, the mercury-laden carrier gas is directed through 2 5-inch cells for high sensitivity optical cells for low concentrations. And then it goes to a single cell, a 1-inch cell, for low sensitivity or high concentrations. And then the light travels through these cells by a reflective mirrors, and then the transient signal is measured at the atomic absorption detector. And then the 2 peaks are integrated against each other, which one's going to be the best fit within that system. So the software will automatically pick the response and apply it to the best fit within the cell, whether it's going to be in the sensitive cell, low concentration, or the non-sensitive cell for the high concentration, based on the calibration and how those peaks are associated with, peaks and response are associated with the calibration. So the use of 2 cells, so the one 5-inch mirrored cell, which becomes a 10-inch cell, and then the short cell is going to provide with the best detection and wider dynamic range than a single cell within any system. Here I'm showing a 1 nanogram per gram or ppb aqueous standard at a 0.5 ml. So what we have is we have 0.5 nanograms of mercury within the system. So that's going to go into the sensitive cell. Therefore, this is measuring everything under the curve here. Here's the least sensitive cell, so it ignores that side of it. So how is this going to improve the productivity within the refineries. So analysis time, dry samples 5 minutes, wet samples 7.5, aqueous about 8.5, max at a 0.5 mils. I really try to limit that though to 0.1 or 0.2 mils within the system. And then I also run an external dryer with that system to help mitigate moisture, transient moisture through the system, which can disrupt the optical cells because water vapor has a myriad of absorbance lines, so you can get slight false positives from the water vapor within the system. So it's important to mitigate that as well. For petroleum distillates, volatile samples, that's about 11 to 12 minutes per sample. So you can also do those, but it takes a bit longer. And with all that said, we have a sample capacity of 70 positions, but we have virtual unlimited. So to put the 5 racks on, and then if operator intervention, you load a rack behind it, you can update the sequence and you can keep going. I have customers that run 100 to 150 samples in a daily run, like for fish tissues and so forth. And that'll give you about 60 samples in 5 hours based on the fastest rate of analysis at 5 minutes. The software. So we have 2 paths for analytical success. We have our standard combustion atomic absorption, and then we also have VHC, which is volatile hydrocarbon. So the difference between these two is CAA is for aqueous, inorganics, and non-volatile samples with high auto-ignition temperatures. The CVAA, VHC mode is for samples that are volatile and low auto-ignition temperatures. So this side of the software, it strictly monitors the injection temperature within the combustion zone. The samples are readied beside the injection port, and when that temperature reaches a preset degrees in centigrade, the sample is going to be injected into the combustion zone. What this will do is it will inadvertently stop the sample from going through its auto ignition at the ones that are low temperature, let's say less than 100 degrees C. So it won't explode or combust outside the combustion zone, losing the sample. It goes into the injection port, the system seals itself up, and then the radiant temperature, the radiant heat from the catalyst zone is going to gradually flow into the combustion zone, and by default, it's going to raise slightly and very slowly up to about 170 degrees C. During that process, the volatile sample is going to go through its auto ignition, and you may hear a faint pop from the explosion within that cell from it combusting. And then it'll go through the regular process after that of drying and then a combustion to remove everything, all the mercury within that combustion zone, pass it through the catalyst and get it loaded onto the cold trap for analysis. So it's a very ingenious type of software platform, which allows our system to be converted for petroleum distillates and volatile sample analysis. So within that software, in both modes, so we can control the decomposition, the catalyst temperature, the amalgamation temperature, and then the times at temperature and so forth. So instrument controls, global settings, injector and auto sampler, gas control detector, the dry temp, with the exception of VHC, that's hard coded in after the radiant heat takes it through its process at 150 degrees C for 60 seconds. And this is in the event that natural temperature rise within the combustion zone did not take it through its auto ignition. I still want to take that auto ignition. I want to be very gentle with that to try to minimize the combustion of that sample, so we don't have any detrimental effect on on the catalyst tube itself, which is quartz. Also, the decomp temp, catalyst temp, lamp on and off, and amalgamation temp, and then you have the calibration. In the sequence tab, this is where you load your samples, and here you have all the control. I mentioned earlier that any type of sample, you can run it unattended. So here's where you can set the sample type, and you can automatically or manually adjust the temperature and gold trap and wait time and dry time for those samples. So you can truly customize your sample load. So if you have a sample that's, say, slightly moisture laden, maybe 10%, you might need a dry time of 30 seconds. If you have a dry inorganic sample, then you don't need a dry time, maybe 1 or 2 seconds. So you can really get the systems to fly through the analysis because everything can be customized. And since we can customize these sample sequence loads with our system, we can do other really innovative type of analysis with the Hydra 2C itself. Basic operation conditions. So drying, less than 30 seconds, 150, catalyst, 600, 30 seconds is a wait time. That's after the combustion is done. That's before the gold amalgamation or the gold trap turns on to liberate the mercury. Just make sure all the mercury passes through the system, through the dryer, and gets attached to the gold trap. Oxygen flow, integration time, and then again, the gold trap heater is set to 630 seconds for that. One thing you got to remember about a system like this is you got to follow the strictest good lab practice, GLP. So wear gloves when handling the standards in the boats. Contamination must be avoided at all costs. You must remember that this is an amalgamation system. So a non-detect in a normal continuous flow system, you wouldn't see it, but here it's all additive. So it loads up onto the gold trap. So small amounts of contamination would be measured and give you a small bias for that sample. So you have to try to avoid that. So I always pre-clean boats and so forth to make sure that's minimized. How do I make my intermediate calibration standards? I start with 1,000 ppm stock solution. I do serial dilutions 1 to 10 across this range, ultimately ending up with a 1 ppb or 0.001 milligram per liter standard. And then what you do is it's mass-based. So you vary the amount of each standard in the boat, and that'll create the calibration. Typically, I go up to 1,000 nanograms, and that's created using the 10 ppb, or I'm sorry, 10 ppm and 100 microliters of that standard. And then I have a typical response of around 900,000 units, and it's measured in the high cell. And here's the cells that are going to be associated with these standards. Here's a calibration that's from a blank to 1,000 with my low standard at 0.1 nanogram. And again, they're mass-based, so it's very simple. You just vary the weights, and then you can have your different masses of mercury within that system. Prior to running calibration and or samples, I should also mention that you only calibrate once, and you don't calibrate again until you have to change a major component within the system, such as the gold trap, the catalyst, or the Nafion dryer. So it'll hold its calibration. I've done experiments where I've calibrated and then changed out a catalyst or a gold trap and run a quality control sample, and it gives me the same response as when the calibration. So it's a very precise unit, and day-to-day activity, it doesn't really change a whole lot. But with that said, it's always nice to check the hardware. You want to make sure functionally it's correct, it's ready to go, the injector works properly, the auto sampler is going to move the boats properly, and they're going to get to the injector, lift it up on the forks. So just a quick check, validate it, and then what I do is I kind of wake up the catalyst. I'm going to use 100 milligrams of flour, and then 100 microliters of DI water in an empty boat, and then I'm going to run that, validate everything, and then run a quality control, and then go ahead and do my sample runs for the most part. And then if you're going to run volatile samples, you should use diatomaceous earth within that boat, or crushed alumina. So that's going to grab the mercury, secure it within the boat so you don't lose it. So it'll help with the loss and integrity of samples. Low range calibration, typically up to 20 or 30 nanograms. You can run linear, quadratic, weight fitted. You can pick and choose the calibration points. You can have multiple points at the same mass. The system is very forgiving with this. But what I like to do is I like to include the 50 nanogram and then run quadratic. So some cases it might dial in the numbers a little bit better. But in this case, we didn't really gain anything on the low end, but on the higher end, we got a little bit tighter. So here we went from 10.4 basically to 10, and the 50 came in at 50.009. The 5 from 5.02 to 4.917. So similar there, but on the other side of the coin. So it all depends on what your comfort level is and what you think is going to be a good calibration to perform your analysis. For the high range, the same thing, typically up to 1,000. Like I said, sometimes I might go up to 1,500 nanograms, but you need to run quadratic. And with this, I use the blank, include the blank in this calibration, and that helps dial it in as well. So here the 50 went from basically 50, 59 to 49 by using that blank. With the rest of it, we didn't gain a whole lot, but some of it is slightly better or about the same. But the main thing is from that 50 to 100 range, it helped in that range right there. So it just depends on when you look at it. You can, like I said, you can pick and choose, and you can delete. So if you have a calibration that standard point that you know was contaminated or it looks odd, you can just delete it from your system, and then you can rerun it later as well. So some of those applicable methods. So US EPA 7473 validation. So that is for solids and solutions. So here, my solutions happen to be residual fuel oil. So I ran 7 replicates, and I achieved 3.94. The certified value is 3.46 plus or minus 0.7. So well within that range. So that's my solution. One of my quality control samples was coal fly ash. So that's the solid. 1005 plus or minus 22. So I achieved 1,034, basically 103%. So one run, one method, 2 different solution types were validated for 7473. For the coal side of it, coal and combustion residues, so the coal combustion residue is the coal fly ash. So that's a validation for 6722. If we move over to the ASTM, the oil method, 7623, so my validation is the residual fuel oil. So one run, running an SRM to validate ASTM 7623 on the system. I also validated 2 other methods, EPA 7473 and ASTM 6722. One run, typically it was probably a little bit over an hour. Here's all the values from the system as well, and then showing one of the, I guess this would be the 1633 coal standard there. I mentioned earlier about some unique applications that we can use the system for, and one of them is that VHC. So on a performance study or laboratory in the Netherlands, Amos Laboratories, they jumped on a performance study and for naphtha, and they achieved a reported value of 26.9 and 26.5 on 2 samples, where the mean was 27.953 and 28.053, and their Z scores were 0.2 or less. And actually, of all the 30 or 35 participants in the study, this system, the Hydra 2C, along with the Amos Laboratories, got the best results and the lowest C score out of all the participants. Another method that's novel to the system could be thermal desorption. So qualitative determination of mercury species and feedstocks. Is it possible to use that? And if so, it's a valuable tool to measure the species of feedstock within the mercury. Therefore, you can model the transport and fate within the refinery. Also, Envoy allows for customization of the event sequence for each sample, which makes thermal desorption possible. So change the drying time, temperature, change combustion time, temperature, integration time, gold trap, etc. So to do the thermal desorption, you set the system parameters, dry time at 100 degrees C, and then catalyst temperature at 500, and then the decomposition temperature at 400 with 1 second. Then you can create a sequence with one sample. And then this is how it works. So you analyze that sample, and then you're going to go back in, and since it's customizable, you can change the dry time. And so start with 100, maybe go to 150, and then you can revise the ID to reflect that change in temperature, and then repeat that analysis. Keep the sample in the boat. You're going to analyze the same sample over and over and over. So it's going to inject, and then so forth. And it's going to take probably about an hour, a little more of an hour, more than an hour, to get all the analysis for each different temperature. So you continue that process. So what happens is, with combustion set to 400 in 1 second, it just blows right through that. So in reality, what I'm doing is I'm using the drying oven as the thermal desorption component and changing the temperature. So here I used the process for coal, fly ash, and marine sediment. So MESS-391 and our same coal fly ash of 1005 nanograms per gram. So overall, the species sum was relatively close to the total mercury value of this run. 600 degrees temperature for the catalyst. I think that the radiant heat affects the thermocouple, therefore the fans are on and it drives down the temperature a little bit more. That's why when we go from 600 to 500, under those low values, at 600 you see less mercury emitted and measured, and it's the same across both sample sets, and that's due to the cooling effect from the fans. I must note here that the system had a failing catalyst. I realized it once my analysis had started, and then I'm like, well, I'm just kicking the tires now, so I'm just going to keep going and see what happens. Otherwise, these values would have been elevated by probably about 10%. And I previously displayed values for the 1633 that was 102 or 103% of the actual value. Here we're achieving 83% and 81% basically at the two different temperatures. Similarly, I've got a slide coming up that's going to show you the value of marine sediment as well. That's going to be pretty much as described in the certified value of that as well. So based on the results, I'm going to deem this experiment as a successful species quantitation. So here are some of the species theoretical values at the different temperatures. So you have mercuric chloride, mercurous chloride, mercury sulfide, and so forth, and mercury sulfate. These are some of the different temperatures. So basically, by the time you hit 400 or 500 degrees, everything should be liberated. Mercury sulfate is the last component that's going to come off. So is it accurate? Somewhat. It's quantitative, but it can give you a good start on what's in that feedstock. So it's kind of a nice feature. Another novel technique that can be applicable to the Hydra 2C is methyl mercury. So extraction. So a novel method was developed by the Korean Ministry of Food and Drug, and it was demonstrated in an application note that we wrote called AN2102, which is available on our website. It applies to all foods and where standard specifications for methyl mercury has been set. It's pretty basic principle analysis. So you're going to pre-treat the sample with sodium chloride, hydrochloric acid, and then toluene. And then you're going to centrifuge that, and then you're going to take the toluene fraction and extract the mercury into an L-cysteine layer, and then that layer is analyzed on the combustion system. And then quantify the methyl mercury is calculated by using mass conversion to elemental mercury and then to methyl mercury from the total mercury that's dry value within the system. So it's pretty much simplified as you run a non-analytical sample to get your moisture, and then you perform the methyl mercury mass conversion using the following formula: A times B divided by C times 1.75. And then the results are in ppb, are a direct conversion in the units from 2 micrograms per liter. So these are results on the system itself. So the results minus the extracted blank right here, and then the volume that you used in the extraction. In my case, I used 50 milliliters, so 0.005 liters, and then divided by the dry rate. And then I'm going to take and multiply that by the total mercury to methyl mercury conversion at 1.075, and that's going to give me my value in methyl mercury micrograms per gram in ppm. So with that said, the experiment I ran for that, I used total mercury in methyl mercury in tuna fish, reference material BCR 4.63, and then here's the extraction weights, percent moisture of the corrected weight. So this is a moisture corrected weight into the system, raw values, and then I ran a control blank through the system. So I subtracted the control blank from the raw value. I ran multiple control blanks to ensure that they were relatively close and they were almost on top of each other. So that's a corrected value. And then the methyl mercury after that conversion, we have percent RSD of 2.85 and an average of 2.81, or 92.4% of the certified value at 3.04. Earlier, I showed that marine sediment that was 70% recovery or so, which I equated to a catalyst that was failing. Here I have the same marine sediment, and my return value is 104% on a completely validated system. This is bovine muscle, and that value is at 91%. So inorganic, organic samples, organic type samples, or I should say tissue samples. And then at the end, I did the average or the total mercury of that sample, which is 228.50 ppb plus or minus 160. And with the moisture corrected value, I got 28.99 or 102%. And here's back to the coal fly ash again at 101%. So with all this data, that's how I can take and back calculate and value and evaluate that thermal desorption experiment success, because I know how the system performs. I know what happened. I know why those values are low. So we can therefore just elevate those values or look at the experiment as a full success. So what are the takeaways from all this? So it's probably possible to use the system for thermal desorption technique to get qualitative results for the inorganic species of mercury and crude and other feedstocks going into the refineries. Is it possible to use the simplified extraction method to get qualitative or qualitative value, I should say, for organic mercury within the system? Alternately, you can use an extraction method such as EPA 3200 for extractable organic and inorganic mercury, and then you can analyze that on the system for total mercury and then just convert the results back to the target species. So again, is it possible to get unspecified qualitative organic mercury determination with that extraction method developed for the food? Is possible. I haven't tried it yet, but then we have alternate options as well. So in summary, the analyzers are applicable to direct combustion applications. They're superior in detection limits for solids and semi-solids as low as 0.01 nanograms per gram. They're adaptable for analysis of extractions. They're also adaptable for exotic analysis such as thermal desorption experiments. You can do a lot with the system. The software is very flexible, and once you know and love your system, you can do lots of things that can give you lots of data about the samples, whether it's species data, organic species, and so forth. Some of the references I use for this presentation and report that was presented here today. So with that said, I would like to thank you for listening. I hope your day and evening goes well. And if you have any questions about what was presented here today, you can simply add them to your login for the presentation, and then they will all get submitted to me. Or if you want to communicate directly with me, my email is jeff.forsberg@teledyne.com. So with that said, thank you very much and enjoy your day.